In this video, we're going to be looking at exponential functions and their behaviors and what happens when we do different things to them. So first of all, what is an exponential function? It's when we have y equals a to the x power, or you could say f of x equals a to the x power. So today we're going to be looking at different functions in this with this formula, where y equals a base 2 to the x power, y equals base 3 to the x power. Also, we could look at what happens when y is equal to 1.5 to the x power, and also what happens when a is less than 1, y equals 1/2 to the x power. Put that in parentheses. Okay, so for all of these graphs, we have to use a value of a that is greater than 0. Okay, so first of all, we're going to start with what happens when we have y equals to the x power. So we first draw a chart to compare these values. And we are going to be using -3, -2, -1, 0, 1, 2, 3 to give us a pretty good idea of what is going to happen. So first we start with 0. When x is 0, we have y equals 2 to the 0, which is 1. Then we have 2 to the first power, 2, 2 squared, 4, 2 cubed, 8. Likewise, when we go this way, we have 2 to the minus 1, which is 1/2. 2 to the minus 2, that would be 1/4, and 2 to the minus 3, 1/8. Notice how these values are related. Okay, so what would this look like if we were to graph them? All right, so now we just start to plot these values. I start with when x is 0, y is 1. When x is 1, y is 2. X is 2, y is 4. X is 3, y is 8. On the other side of the y-axis, we see that it starts to decrease. When x is -1, we have 1/2. -2, 1/4, -3, 1/8. And so then we just sketch in this graph. We can see as x becomes more negative, the graph approaches the x-axis, but it never touches it. So in this case, we would say that x is the asymptote for the function of 2 to the x power. X is the asymptote. So now we want to see what happens when we have a different base, like y equals 3 to the x power. So again, we make a chart to see what will happen when we have the same values for x. And we just use 3 as the base. So starting with 0, 3 to the 0 is 1. 3 to 1, 3. 3 squared, 9. 3 cubed, 27. We know how this is going to behave on this side. We use the same values. We have to the -1 power would be 1/3. -2, 1/9. And -3, 1/27. So if we would graph this on the same chart, you'll see something interesting. We'll do this in red. So these values we will graph with red, starting with when x is 0, y is 1 again. When x is 1, y is 3, x is 2, y is 9. That would be way up here. And x is 3, it would be off of our chart. Going negative, we have 1/9, so that would be below 1/2, close to the x-axis. this was 1/3. The next one to the -2 is 1/9. -3, 1/27. Close to the x-axis again, but not crossing. So as we sketch this graph of 3 to the x power, we see that it has a similar behavior, but we see that it is closer to the y-axis and it dips below on the negative numbers. Also, x would be the asymptote for this situation. Okay, so next situation, let's find the values for y equals 1.5 to the x. So we have x and y. We find all of those values. Okay, I want you guys to do this with me. Again, we start with -3, -2. Starting with 0, 1.5 to the 0 power would be 1. 1.5 to the 1, 1.5. 1.5 squared would be, 2.25. And 1.5 cubed would be 3.375. Then going to the -1, see how these values start to decrease. I have to the -1 would be 0.6 repeating. To the -2, 0.4 repeating. And to the -3, 0.296 repeating. So in all of these cases, we see the values continue to decrease when x is negative and increase when x is positive. Now, before I graph this, I would like you to think, how would this graph look? We can see y equals 2 on the first graph. Y equals 2 to the x. And then when we increase this coefficient to y equals 3, we see that it is closer to the y-axis. So what would you expect for this following graph? Y equals 1.5 to the x. So let's plot the values and see if it is what we expect. Again, I'll do this in red. So here we have y equals 1.5x. So at 0, again, it crosses at 1. At 1, we are at 1.5. We see that these values then are on the other side of the first graph that we created. So at 2, it's 2.25, which is about right there. And at x equals 3, 3.375, so that would be less than 4, about right here. Then going to the negative values, we see it decreases, so we would be then on the other side of the y equals 3x, and on the other side of y equals 2 to the x power. 0.6 repeating, 0.4 repeating, 0.296 repeating. So then if we go and sketch this, see that this graph has a similar behavior, crossing again at y equals 1, but then on the negative values for x, it is above the previous graph. If we continue to plug in more negative values for x, we would see that this would also be approaching the x-axis, calling it the asymptote. Okay, so for the last graph we have here, y equals 1/2 to the x power. We'll do the same procedure again, and we'll see what behavior this will have. Okay, so again, we start with when x is 0, y would be 1. Then we have when x is 1, 1/2 to the first power would be just 1/2. So I'm going to put 1/2. Then we have 1/2 squared, that would be 1/4. And 1/2 cubed would be 1/8. Then on this opposite side, if we'd be using a negative value of x, we see that it would have the opposite behavior of the right side. So we have 1/2 to the -1 power, so that would then become 2. 1/2 to the -2 power, we see 4. And 1/2 to the -3 power, we see 8. So if you look at this graph, you can see it is related to our first graph, just it is the reflection. So let's graph this on the same graph. Y equals 1/2. So again, we see that it is crossing where y equals 1. when x is 1, y is 1/2. X is 2, 1/4. X is 3, 1/8. And then to the negative values, we have -1, value of 2, -2, 4, and -3, 8. When we sketch this and we compare it to the graphs on the other side, it appears to be a reflection. In fact, looking at the values, it is a reflection of the graph of y equals 2x. So we can determine something by looking at this graph. When a has a value that is less than 1, but greater than 0, we will see the behavior increasing in this other axis. When a is greater than 1, they will be increasing in the positive x-axis. Now that we've seen basic behaviors of exponential functions, we're going to look at different transformations and what happens when we have a transformation and we want to be able to draw these graphs without having to make a table of values. So first we remember how the behavior of y equals base 2 to the x power looks in a graph. So will increase towards the right and decrease towards the left with the x as the asymptote. So what happens when we do something to this formula? So first of all, we're going to look at reflections. So reflections occur when we do something by do something to the coefficient or to the exponent. So we're going to look at two different cases first. So we have case 1, where y equals 2 to the minus x. And then we're going to look at case 2, where we have y equals -2 to the x. So first of all, we're going to look at case 1, where we know that f of x in the previous case equals 2 to the x. What are we doing to this formula? We are evaluating f of -x. So when we have f of -x, this causes a reflection in the y-axis. So if we were to graph this, where previously we have this behavior, where x crosses at 1, we know that if we would put a -1, it would be going to graph this in red. If we would use the same values for y, the x values would be the opposite. So if we'd have 2 to the -1, 2, we would see this opposite behavior, or a reflection into the y-axis, over the y-axis. So in the second case, we see that we are multiplying the function by a -1. So in fact, we have a negative f of x, and this will cause a behavior where we reflect in the x-axis. So again, start with the same graph. With our original function. This would be reflecting then over the x-axis. And we would have, when x is 0, y would be -1. So we would see a behavior reflected over the x-axis. So in these types of cases, it's a reflection. We have the same values, just that they would be reflected over the y-axis in the first case when we have the negative exponent, and when we have the coefficient times a -1, it would be a reflection over the x-axis. So the next case that we're going to see are called translations. So we're going to be looking at 4 different cases. The first case we have is when we have the function, again, 2 to the x, but then we add 2. And the second of this type is when we have 2 to the x, but we subtract a value, let's say -1. So in the case of this type of translation, we are adding something to the function. We have f of x plus a. This gives us a translation of a units parallel to the y-axis. So depending on what is a, it will be moving that many units parallel to the y-axis. So in the first case, case 1, the graph of our original 2 to the x would be moving up 2 units. So how would this look? We start with our original, where y equals 2 to the x. Our graph then, for this first case, would be moving up by 2 units. So where y is 1 previously, it would be adding 2, 2, 3, and it would have exactly the same behavior as y equals 2x. So in this case, you're wondering what would be the asymptote for this new situation. Whereas the asymptote for y equals 2x was on the x-axis, we would say that the asymptote for this would be when y equals 2. So you can draw this with a dashed line. So then we have the second case where y equals 2x minus 1. You can already guess what is going to happen to this graph. So we have a -1. So the graph will be moving down by 1 unit. By 1 unit. So again, we'll graph this one in red. So before, where it was crossing at y equals 1, it would be crossing at where y equals 0, and it would have the same behavior as y equals 2x. Continuing down in the negative x. And so the question would be, where would be the asymptote? Since we're moving down by 1 unit, the asymptote then would be where y equals -1. So then we have another type of translation. We have another type of translation in the following 2 formulas. So this is where we add or we subtract something to the exponent. So we have y equals 2 to the x minus 2 power. So here you can see that we are subtracting 2 from the value of x. And in case 4, where y equals 2, to the then if we add something to the exponent. So here in case 3, we see that we are subtracting 2 from that x. And in case 4, we're adding to that x. So we'd be writing then our function of x plus a would give us a new type of translation. So in case 3, we have our function of x minus 2. And in our case 4, we have our function of x plus 1. So how would this affect our graph? The rule is then that it would be a translation negative a or minus a units. Okay, so how would this look in comparison to our original graph? So again, we look at our original graph of y equals 2 to the x, crossing at 1. And so in situation 3, we see that it is moving negative a units. So where a is -2, the translation would be a -2, following this rule, a -2. So it would be moving to the right on this axis. It would be moving to the right on the x-axis. So we would have a value at 1, and it would have the same pattern, but we see that it is moved towards the right, and it follows the same behavior. And what would happen in the case 4, we see that it's +1. So if it is moving minus a units, we have a a equals 1. So that means it would be moving -1 units, moving that graph towards the left. So here we have case 3, which is y equals 2 to the x minus 2. And in the other case, we'd have the value of 1 here. And we see that we're taking our original graph and it's moving this way towards the left with the same asymptote of the x-axis. So now you're wondering, what values do we find on the y-axis to say where is this new formula crossing the y-axis, or you could just put where x equals 0, so for case 3. So now you're wondering, where would these graphs be crossing the y-axis? So in the case for case 3, we have y equals 2, and we'll just plug in 0 for x to the minus 2. So we'd have 2 to the -2 power, which would be equal to 1/4, be crossing at y equals 1/4 when x is 0. And in case 4, where would that be crossing the y-axis? We have y equals 2 to the x plus 1. So we plug in 0 for x, 2 to the 0 plus 1, which is equal to 2. So for the graph number 4, it would be crossing at 0, 2. So the next type of transformation that we're going to be looking at is called a stretch. So this is a different situation, stretches. So as you can guess by the name, it will be either stretched vertically or stretched horizontally. So I'm going to write down 4 cases quickly. We have case 1 for stretch, y equals 2 to the 2 times x. So here we're changing what is the exponent, so 2 times x. And the other case of that type of stretch where y equals 2 to the x over 2, or dividing that exponent by something. And the other 2 cases we have, case 3, is where we multiply the coefficient times a value. So here we have times 2. And case 4, then if we are multiplying by a value less than 1, so here we'll do it times 1/2. So what will happen in these cases? In case 1 and case 2, we will have a stretch. So we say the function of x is being multiplied by a number. We know that the function of x is multiplied by something, so we say the function of ax will cause a stretch with a scale factor 1 over a parallel to the x-axis. So what does this mean? We will be seeing a stretch of the original graph in this direction. Be stretching towards the left and towards the right. So we will see that the x distance will be affected while the y distance will be staying the same. In the case of formulas 3 and 4, we see that we have a value times the original graph that we have. So this would be a value times our original function, and this will also cause a stretch of a scale factor of a. but this stretch will be parallel to the y-axis. So what would this look like? We would be taking our original graphs and it will be stretched vertically, so either making it longer in appearance up and down, or it would be making it shorter. Okay, so first looking at case number 1, we're going to be comparing this with our original graph. Where we have the crossing point at y equals 1. So what is going to happen in this first case, we have a stretch of a scale factor of 1 over a. So in this case, we have 2. So our stretch factor would be 1 over 2. So the distance would be halved. By 1 over 2. So what would this look like? We would also have the same value crossing when x is 0, but for every value of x, it would then be halved. In the negative values, it would be crossing below our original. And what would happen in our second case, where we have a 1/2 times that, so 1 over 1/2 would give us a factor of 2, or so it would be doubled, so that would be times 2. So what would this look like? Again, it would cross at y equals 1, and this graph would then be dipping below by a factor of 2. So for every x, it's going to be times 2. Same for y, and it would be above the original graph. So then, for the last cases, we have case 3 and case 4. Again, we want to see what behavior they will be showing on a graph. Starting with the original, y equals 2x. We look at the coefficient here, 2 times the function, so it would be stretched on a scale factor of 2 times this value. So this would be doubled in the y direction. So here we would see that when x equals 0, we'd have 2 to the 0 power 1. 1 times 2, we would see that it would be crossing the y-axis at 2. So then for every value we have, it would be increasing by double that amount and have the same characteristic towards the left, towards the negative x. So what happens in our case 4, where we have these values times 1/2, everything would be halved, where we would see in this graph, we'd have when x equals 0, we'd have 1/2 times 1. It would be crossing at 1/2 and have a rise that is less drastic and decreasing on this side. Okay, so thanks for watching. If you have any questions, let us know.